Hello. In this example, we'll calculate the plastic moment of an I-shaped beam section that is built up by welding a 6-inch by 1-inch top flange and a 10-inch by 1-inch bottom flange to a 20-inch by ½ inch web. All steel in this section has a yield stress of 50 ksi. The first step in the process is to locate the plastic neutral axis, and then the second step is to calculate the plastic moment itself. We'll conclude by discussing the plastic section modulus for the cross-section and different options that are available for different types of cross-sections. This example builds off of earlier example problems where we examined the elastic bending properties of this section, including the moment of inertia and normal stresses resulting from a bending moment of 600 kip-feet, and another example where we calculated the plastic moment of a similar but doubly symmetric cross-section. If you haven't worked through those examples yet, you can watch them by clicking on the link shown on this slide. The plastic neutral axis of a cross-section can always be found by assuming that the elements in the cross-section have reached their yield stress and then finding the point in the section where the forces above that point would be equal to the forces below that point. If we assume that the plastic neutral axis is located in the web of this I-shaped cross-section, then we can use the notation y bar sub pw to denote the location of the plastic neutral axis relative to the top of the web of the section, which is mathematically more convenient in cases like this than using the top of the cross-section as a reference point or datum. And then we can write this equation, where the sum of the plastic force resultants in the top flange and in the area of the web above the plastic neutral axis is equal to the sum of the plastic force resultants in the area of the web below the plastic neutral axis and in the bottom flange. We can illustrate that process here, where we'll sketch a short length of the beam in elevation next to the sketch of the cross-section. If we assume that a positive bending moment is applied, it looks like a double-headed vector acting on the cross-section, with the heads of the vector pointing to the left, which, per the right-hand rule, indicate that compression is acting at the top of the section. The same bending moment can be illustrated by using a pair of curly moment vectors applied to the length of the beam shown in elevation, which again indicate that compression is acting at the top of the section. With that, and assuming that all of the elements are loaded to their yield stress, the distribution of stresses on the section would look like this. This is referred to as a plastic stress distribution. Finally, the force resultants in the top flange, the area of the web above the plastic neutral axis, the area of the web below the plastic neutral axis, and in the bottom flange can be drawn like this. If we have selected the correct location for the plastic neutral axis, then the sum of the force resultants above the plastic neutral axis will be equal to the sum of the force resultants below the plastic neutral axis, at least for the case of a beam with no axial force. This neutral axis for the plastic stress distribution is where the stresses change from compression to tension in the cross-section. With the assumption that the plastic neutral axis is in the web of the section, we'll start off by finding the magnitudes of the resultants in each of the elements when the cross-section has reached its fully plastic state. The top flange has an area of 6 square inches, so we can write that the plastic force resultant in the top flange, P sub Ft, is equal to 50 ksi times 6 inches squared, or 300 kips. Next, we can write an expression for the area of the web above the plastic neutral axis, A sub Wa, as a function of the location of the plastic neutral axis, y bar sub Pw. Then we can write that the plastic force resultant in the web above the plastic neutral axis, P sub Wa, is equal to 25 times y bar sub Pw, where the value of 25 carries units of kips per inch. Next, we can write an expression for the area of the web below the plastic neutral axis, A sub Wb, also as a function of y bar sub Pw. And then we can write that the plastic force resultant in the web below the plastic neutral axis, P sub Wb, is equal to 500 kips minus 25 kips per inch times y bar sub Pw. Finally, we see that the bottom flange has an area of 10 square inches, so we can write that the plastic force resultant in the bottom flange, P sub Fb, is equal to 50 ksi times 10 inches squared, or 500 kips. If we assume that the plastic neutral axis is in the web, then we can write that P sub Ft plus P sub Wa is equal to P sub Wb plus P sub Fb. Substituting the values for the plastic force resultants that we found on the previous slide, we can solve for the location of the plastic neutral axis y bar sub pw. As a check, we see that our initial assumption that the plastic neutral axis was in the web is validated since the value of y bar sub pw that we found falls between 0 inches and 20 inches. Next, if we want to, we can find the location of the plastic neutral axis relative to a more conventional datum. Here, I'll show that the location of the plastic neutral axis is 15 inches measured from the top of the steel cross-section using the notation y bar sub p. Note that I use the notation y bar sub p to indicate that the distance is measured from the top of the cross-section, and I use the notation y bar sub pw to indicate that the distance is measured more conveniently from the top of the web of the section. At this point, we can calculate the depth of the web below the plastic neutral axis and find that it is equal to 6 inches. Then we can calculate the area of the web above the plastic neutral axis and find that it's equal to 7 square inches. And finally, we can calculate the area of the web below the plastic neutral axis and find that it is equal to 3 square inches. After the location of the plastic neutral axis has been determined, the magnitude of the plastic moment can be calculated. The plastic moment of a cross-section can always be found by summing the moments that the force resultants of a fully plastic section create about some point. We often choose to sum those moments about the plastic neutral axis of the cross-section. In this equation, m sub p is the plastic moment and p sub I is the plastic force resultant of each element in the cross-section. We often choose to sum the moments about the plastic neutral axis itself, and when we do that, d sub I is a distance measured from each of the plastic force resultants to the plastic neutral axis. Returning to our sketch of the plastic stress distribution, we can add those dimensions to the cross-section now. First, we recognize that since the force resultants acting in the top flange represent a uniform stress block, that its line of action passes through the centroid of the flange, which is located 14.5 inches above the plastic neutral axis. Similarly, since the force resultant acting in the web above the plastic neutral axis also represents a uniform stress block, its line of action passes through the centroid of that area, which is located 7 inches above the plastic neutral axis. We also note that the line of action of the force resultant acting in the web below the plastic neutral axis passes through the centroid of that area, which is located 3 inches below the plastic neutral axis. And finally, we note that the line of action of the force resultant acting in the bottom flange passes through the centroid of the bottom flange, which is located 6.5 inches below the plastic neutral axis. Next, we'll move things around a little bit to give ourselves more space to work, and we can calculate the force resultant in the top flange as 50 ksi times a flange width of 6 inches times a flange thickness of 1 inch, which is equal to 300 kips. Next, we can calculate the force resultant in the web above the plastic neutral axis as 50 ksi times the depth of the web above the plastic neutral axis, 14 inches in this case, times the web thickness of 1/2 inch, which is all equal to 350 kips. Next, we can calculate the force resultant in the web below the plastic neutral axis as 50 ksi times the depth of the web below the plastic neutral axis, 6 inches in this case, times the web thickness of 1/2 inch, which all equals 150 kips. And then we can calculate the force resultant in the bottom flange as 50 ksi times a flange width of 10 inches times a flange thickness of 1 inch, which is equal to 500 kips. Finally, we can confirm that the sum of the forces above the plastic neutral axis and the sum of the forces below the plastic neutral axis are equal. They both equal 650 kips, which indicates that the plastic neutral axis is in fact located 14 inches below the top of the web, or 15 inches below the top of the cross-section. Next, we'll label each of the plastic force resultants explicitly, and then we can calculate the moment created by the plastic force resultant in the top flange about the plastic neutral axis, which is equal to 300 kips times the distance of 14.5 inches, or 4,350 kip inches. Then we can calculate the moment created by the plastic force resultant in the web above the plastic neutral axis, which is 350 kips times the distance of 7 inches, or 2,450 kip inches. Next, we can calculate the moment created by the plastic force resultant in the web below the plastic neutral axis, which is 150 kips times a distance of 3 inches, or 450 kip inches. And then finally, we can calculate the moment created by the plastic force resultant in the bottom flange, which is 500 kips times the distance of 6.5 inches, or 3,250 kip inches. Note that even though 2 of the plastic force resultants are acting to the left and 2 are acting to the right, that they all act to create a counterclockwise moment about the plastic neutral axis. Thus, they are all treated as positive. The next step is to sum the moments that each of these resultants create about the plastic neutral axis, and we find that the plastic moment is equal to 10,500 kip inches, or 875 kip feet. As a final step, we can calculate the plastic section modulus Z by dividing the plastic moment by the yield stress. For this section, we find that the plastic section modulus is equal to 10,500 kip inches divided by 50 ksi, or 210 inches cubed. Note that it only makes sense to calculate a plastic section modulus for a homogeneous section where the yield stress is constant throughout the cross-section. It doesn't make much sense to calculate a plastic section modulus for a hybrid section since there are at least 2 different values of f sub y in the section, and it isn't obvious which of those values of f sub y should be used in the calculation. At this point, let me show you a shortcut that I often use for finding the plastic neutral axis in an I-shaped section. We'll start again with the assumption that the plastic neutral axis is located in the web of the section, and then we'll write equations for the plastic force resultants for each of the cross-sectional elements like we did before. However, instead of breaking the web into 2 parts, one for the part above the plastic neutral axis and one for the part below, I'll simply calculate the force resultant for the whole web at its yield stress. I'll call this P sub W, which is short for P sub web. Next, I'll define a new variable Q, and I'll let it represent the percentage of the web that lies above the plastic neutral axis, and, if we're under a positive bending moment, is carrying compression along with the top flange. Thus, we can write that the force carried by the web above the plastic neutral axis, P sub WA, is equal to Q times P sub W, and we can write that the force carried by the web below the plastic neutral axis, P sub WB, is the remaining part of the web force equal to 1 minus Q times P sub W. As an extension of that, we can write that the area of the web above the plastic neutral axis, A sub WA, is equal to Q times A sub W, and that the remaining area of the web, the part that lies below the plastic neutral axis, is equal to 1 minus Q times A sub W. With the assumption that the plastic neutral axis is in the web of the section, we can again write that P sub Ft plus P sub Wa is equal to P sub Wb plus P sub Fb. If we substitute Q times P sub W for P sub Wa, and if we substitute 1 minus Q times P sub W for P sub Wb into that equation, and if we then substitute numeric values for P sub Ft, P sub W, and P sub Fb, we can then solve for Q, the portion of the web that is above the plastic neutral axis, and find in this case that Q is equal to 0.7. This means that 70% of the web is above the plastic neutral axis when there is a plastic moment, and 30% of the web is below the plastic neutral axis. Or, another way of looking at it is that if there was a positive bending moment in the beam, that 70% of the web is in compression and 30% of the web is in tension when the beam is at its plastic state. Since the value of Q that we found is between 0 and 1, this validates our initial assumption that the plastic neutral axis was in fact in the web of the section. And we can now solve for the location of the plastic neutral axis, y bar sub PW, measured from the top of the web. And then we can solve for the area of the web above the plastic neutral axis, A sub WA, and we can solve for the area of the web below the plastic neutral axis, A sub WB. So, is this approach for finding the location of the plastic neutral axis any better than the formal approach that we used earlier? Maybe, maybe not. Personally, I prefer this approach because I feel like it results in a more compact set of calculations than the other more formal approach. However, I recognize that this may be a bit more abstract than the formal approach, particularly when you're first working these types of problems, especially when you're using a made-up variable, lowercase q. Ultimately, the choice is up to you. Earlier in this example, I said that the plastic neutral axis of a cross-section can always be found by assuming that the elements in the cross-section have reached their yield stress, and then finding the point in the section where the forces above that point would be equal to the forces below that point. That is true, and personally, I like that approach since it always works. However, let me show you another approach that can be used for this problem. This cross-section is homogeneous, meaning that all of the elements in the cross-section have the same yield stress. Since the cross-section is homogeneous, we have the option of finding the plastic neutral axis and determining the plastic section modulus by working directly with the areas of the elements in the cross-section instead of working with the plastic force resultants of the elements in the cross-section. In a homogeneous section, the plastic neutral axis is located where the area above the axis is equal to the area below it. This concept is sometimes referred to as the equal area axis theorem, and the equation shown on this slide holds for an eye-shaped homogeneous section where the plastic neutral axis is in the web. Based on this idea, we can write an equation setting the area of the cross-section above the plastic neutral axis equal to the area of the cross-section below the plastic neutral axis, where the terms a sub wa and a sub wb are both functions of y bar sub pw. And then we can solve for y bar sub pw to determine the location of the plastic neutral axis. If you're so inclined, you can also use the shortcut that we discussed earlier, where we use the term Q, defined as the portion of the web above the plastic neutral axis, with the equal area axis theorem to make the calculations more compact. While the plastic moment of any cross-section can be found by summing the moments that the force resultants of a fully plastic section create about some point, the plastic section modulus of a homogeneous section can be found directly by summing the moments that each of the areas of the elements of the cross-section create about some point. Here, we calculate the distances from each of the centroids of each of the cross-sectional elements to the plastic neutral axis of the cross-section. And on this slide, we multiply those distances by the corresponding areas to find the moment that each of the areas of the elements in the cross-section create about the plastic neutral axis. We sum those moments for each of the four cross-sectional elements to find the plastic section modulus Z. This is Z sub x, since the plastic section modulus is for bending about the x-axis of the cross-section. Finally, we calculate the plastic moment for the cross-section by multiplying F sub y and Z sub x. Taking 50 ksi times 210 inches cubed, we find that the plastic moment is equal to 10,500 kip inches, or 875 kip feet. In summary, we calculated the location of the plastic neutral axis and found it to be located 15 inches from the top of the cross-section, or 14 inches from the top of the web. Then we went on to find the plastic moment of the cross-section to be 875 kip feet and the plastic section modulus to be 210 inches cubed. Since this was a homogeneous cross-section where all of the cross-sectional elements had the same yield strength, we were able to perform those calculations using two approaches. First, by working with the force resultants on the fully plastic section, and then by working directly with the areas of the cross-sectional elements. Had this been a hybrid cross-section instead of a homogeneous cross-section, then we would not have been able to work directly with the areas of the cross-sectional elements. We would have had no choice but to work with the force resultants on the fully plastic section. Another interesting thing to note about this cross-section is that when we compare the fully plastic stress distribution, shown here in the middle, to the elastic stress distribution, shown here on the right, we see that the location of the neutral axis is different. In a cross-section like this, where there is only one axis of symmetry, the location of the neutral axis changes as the material in the cross-section yields and the distribution of stress approaches a fully plastic condition. This would also be true for a doubly symmetric but hybrid cross-section if we were to consider such a problem.